And our next speaker is Umberto Cherubini from University of Bologna.
Thank you. Thanks a lot for having me here. I visited Peter in 2019 and now in October and November 2021, we completed 4 papers plus an idea that he left on January 17 when we had our last talk. The paper is I'm presenting the paper that I think is our best paper together, is the best of my papers for sure, and it's about Kelly. It's the only paper of my life in investment science. I think also is the only one in Peter's literature, even though I mean it's not finite, so I cannot be sure. But we prove in this paper that under some conditions, what we learned in a textbook, in financial economic textbook, and we also had in the presentation by Jim gathered this morning, so that the growth optimal portfolio, the portfolio maximize the expected log of wealth, is actually may not actually be true. You have to make the plural, because you may have more growth optimal portfolios. Okay, just to introduce this must be Peter in the 90s, when we first came across, early 90s, more or less when I also met Eliette, but I met Eliette in person, while Peter, for some reason, I met just in a mail and not email, ad mail. Okay, I was thinking in this day how we came across what we were doing. I in Milan, and Peter here in the US. We were working on delivery options in bond future contracts, and we didn't have. At least I didn't have internet, but in any case, I managed to. Or he wrote us a letter on our paper, and so we began to exchange ideas by hard mail. Okay, our interest had been a cointegrated process. I mean, stochastic, but common stochastic trend. And so I was quite surprised when I came here in September, October 19. I discovered that we were still on the same random page, very different from the page of the 90s, but again with the same interest. It was in generalized algebra. You have seen a lot of presentations on this. Da Costa, Pasquale, Cirillo, Salvatore, okay, lot of presentations of this kind. So this is going to make easier my presentation. However, we found out that we were actually haunted by the same Ghost were the work by Axel that I have 66 I saw in the presentation before an earlier paper. Pap, there was the guy there is the guy that is currently working on this. And in the middle, being expert in copulas, I have a lot of results on Archimedean copulas that are in the same line of research, generalized algebra, so distorting algebra. And the point that we had in common, we were both interested in the fact that if you have an associative operation, you may write it in terms of a generator. So we were interested in generators, okay? And the only difference between me and him, the only kind of argument we could have is that he was fond of pseudo addition, I was fond of pseudo multiplication. Coming from copula function theory, someone talked about Archimedean copula. Archimedean copula are pseudo multiplication. Okay, so they're distortion of a product. So I tend to use a pseudo multiplication, while Peter, that was after applying these to solving the early exercise problem in options, was after pseudo sum. Okay. So for this reason, we decided to call the session that we were going to have at Italian Society of Probability and Mathematical Statistics in a couple of weeks, in Peter's memory, option algebras and probability. Okay, because algebra, the algebraic distortion was actually his main interest. So when I understood, so I'm not formally presenting a paper, I just show you how we made it, okay, meeting after meeting. So after I discovered that we were on the same random page that was generalized algebra, I showed him my favorite generalized algebra, or the generalized algebra that I know more. Which is is used in physics, and it's called Salis algebra. Okay, you redefine the exponential function, you redefine the logarithmic function, you get the product and the sum in the same way as Pasquale Cirillo explained yesterday. The point that this is a crossroad of almost everything, as you can see, because the exponential is actually similar to a moment generating function of a gamma distribution, and so we use a lot the gamma distribution. If you take the inverse, you get the isoelastic utility that you are taught at school in financial economics. If you take the Salis, the product, you get you say that C and Y are in the unit interval, you get Clayton copula. Okay, an Archimedean copula. If you take the pseudo sum, you get Sugeno measure, which is a fuzzy measure that I used in the 90s to do Choquet pricing. Okay, to get buyer and seller prices from Choquet pricing. So when I discovered this, I actually realized that I had spent half of my life on sum and half of my life on product, and that was on one side reductive. However, then we went, I showed him another thing that I was actually, I was given by a co-author of mine, a paper on Maslow, in which he reports a theorem by Kolmogorov on a general representation of average. Okay, and so I said, well, I got this in this paper of Maso. I also know this paper. So we were on the same page of the same paper again. And so here, using the same generator, you may actually write a generalized average in which you simply take the generator and inside you have the linear average of the inverse of the generator. Okay, if you take the exponential, you get the log. The inverse is the log, and you get the geometric mean. Okay, this is the definition of regular average in Kolmogorov. And so, having said this, we decided to apply this starting from the pure mathematics, pure mathematical results to the Carry problem. Okay, and as you know, the Carry problem is only based on compounding. Okay, as we are going to see in a minute, everything that rules is compounded. The fact that you reinvest your profits and your gross returns. Okay, and you do that asymptotically. Okay. So we are generalizing a compounding function, okay, which again can be written as exponential of the sum of log, but I can replace the exponential by a generator of a sum of a product. In this case, is the same. You get the same result, and you get a generalization. Okay, you could try here, for example, that Salis generator. Okay, obviously now the result is easy, but what's not easy is to understand the economic meaning behind the generator that you are selecting. However, before doing that, let's review the standard very simplified derivation of the Carry criterion. You have to, your problem is to repeatedly bet on a favorable game. So probability P of winning is greater than probability Q of losing. And the key element of the Carry paper, Carry and Shannon actually paper, is to turn this into something to which the law of large number applies. Okay, so since you are geometrically compounding your return, you take the log. Okay, you take the log, you let the law of large number act on the log, and then you maximize. Okay, and you get the famous Carry solution. If you plug the Carry solution inside there, you get at the maximum minus Shannon entropy plus a constant. Okay, so this is the idea. It's very easy to generalize this if you have in mind other algebras. And so, of course, let me just say that let me just leave the word to Carry that said that actually only it needs is compounding. It only needs the fact that this is the logarithm which is additive in repeated bets and to which the law of large number applies. Okay, so this was the point made by Carry. On the other side, there were Samuelson and Umberto and others were definitely against this solution, stating that, of course, there is a parameter missing, and this parameter has to do with the risk aversion of the individual. Okay, and so there is a very long-standing debate. Poison debate in the works of Peter in this between people from information theory that were using only the law of large number and people from economics that were using only expected utility theory. So from a mathematical point of view, we can easily generalize Carry now. I take any new algebra. I select the logarithm, so the inverse of the generator, and I get and I do the same as Carry. And if you take the Salis algebra, you get actually you get the power utility function. So you get Samuelson's utility function without using expected utility, and that's the point. Okay, so at this point we had realized that we had been taken back to this very old discussion between economists and information theorists. And what we had done, we had used the standard Carry and the Salis algebra, and we had obtained a function like Samuelson function without using expected utility. Okay, that was the idea. The novelty with respect to both the information theorists and economists is that now the growth optimal portfolio may be maximization of the expected log of wealth, or maximization of isoelastic function of wealth. Okay, so it's not only one definition for the growth optimal portfolio. Okay, just a comment. The discussion is not over. Actually, as of today, the same discussion between information theorists and economist is between ergodicity economics, which is a branch of sort of proposal from econophysics on one side and economics on the other side. Okay, and we actually were invited to present these at just in the day of the last Zoom that I had with Peter. I was invited to give a speech at the conference of ergodicity economics in London. Okay. Now the point is now we have good mathematics. We need an economic argument supporting this. I visited Salis in Rio several years ago, and he actually told me that his algebra was meant to represent stars, million light years one from the other, that would move in the same direction. So he had an idea of the universe in mind. So at least we had to have an idea of the economic of these element. So what I did, there was an idea from me and a proof from Peter. Okay, my idea was to put together the compounding idea that is the basic basic pillar of Carry. Okay, and so I can write the compounding as a gross return exponential of continuous time return times a period of time. Okay, with a representation of copulas that everybody that deals with copula has in mind, which is the Marshall-Hawkins representation of Archimedean copulas. Okay, so that uses Laplace transform, and so moment generating function in this case. And the idea is simply that you condition on a given scenario of the random variable, and then you integrate. And when you integrate, you get the moment generating function evaluated at the continuous time return. Okay. And so this was the idea. With that psi, that moment generating function actually was a generalization of our model. And what was the random variable? It was the stochastic clock. Okay, it was a random variable representing delta t that can be more than 1 week, less than 1 week if delta t is 1 week. Is a random variable. At this point, I was in trouble because I was focused on the proof of a Marshall-Hawkins proof that was made on a single random variable z for all the assets. Okay, and once, so I talked to Peter, giving a brief definition, description of the Marshall-Hawkins proof, and in a morning it came out with a proof of the Marshall-Hawkins theorem in a setting which you have a set of IID random variable representing the time, the stochastic time increments. So our setting at this point was a time interval partitioned into n uniform interval, and with n stochastic variable IID representing time increments. Okay, and now the point was to come up with the joint Laplace transform of the joint moment generating function of these with respect to this set of random variable, which is the proof, which is the strategy followed by Marshall-Hawkins in the representation of Archimedean copulas, and this is the version of Marshall-Hawkins in the proof by Peter. This follows. This is a complete proof for the Marshall-Hawkins. In the Marshall-Hawkins case, Z, E, Zi are the same random variable. Okay, here they are independent random variable. And what is interesting is that what you get in the end is actually a Kolmogorov mean in which the generator is the generator of the stochastic clock. Okay, so if you now raise everything to the power of 1 over n, you get the geometric mean of the return on the wealth is actually represented by a Kolmogorov mean, and the generator has to do with the stochastic clock. And then at this point, you have a model in which, given a distribution for a stochastic clock, you get actually a suitable average of the average return. Okay, and then if you want to apply Kelly, you take the inverse of that and you apply Kelly given regularity condition on these inverse generalized log functions, as we call them. So if you now want to get to Salis, just take the gamma, okay, gamma increments for the stochastic clock, and then you have you get the moment generating function of a gamma random variable. You take the inverse of that, and you get the sort of isoelastic like utility function. The difference being that now the parameter has nothing to do with risk aversion, with relative risk aversion. The parameter there now is actually minus theta, and theta is the variance of the clock. Actually, the variance divided by the mean square, and we set the mean on delta t. Okay, so you get a model that is mimicking exactly the Samuelson function, there is elastic utility, but the parameter doesn't have to do with risk aversion. It is the variance of the clock. Okay. Then I came back just before the pandemic, and we decided to close the paper, and we decided to try another clock. And so where another natural choice was the inverse Gaussian at the clock. If you take the inverse Gaussian, what you get is that you get immediately a quadratic utility. So you get Markowitz-like quadratic utility. Notice that the parameter 1 over theta is the variance of the clock in the inverse Gaussian. Okay, as gamma goes to infinity, the variance goes to 0, and you get you are back at the standard log utility. So summary: if you assume that the market has IID stochastic clock dynamics, the compounding is no longer geometric, it's represented by a Kolmogorov mean. Typically, you cannot reach asymptotically the maximization of expected log of wealth. Because it's like, I mean, the variance of the clock keeps you below that. If you take two very well-known models of stochastic clocks, the variance gamma and the inverse Gaussian, you find the result of mimicking two very well-known models of utility theory. So the power utility and the mean variance utility. And this is all for the presentation. Just let me give you a couple of words on the other ideas, the other papers with Peter that allowed me to comment on something that I heard in previous presentation. Peter proposed a copula, and you see that this is an Archimedean copula in which the element is a pseudo sum. Okay, so the idea is that you can actually compound a generator with another generator, and so this gives you a lot of freedom in terms of choosing the generator. And in fact, we have another paper in which we price options with generator, and we generate the smiles accordingly. Thank you. That's all.
Thank you very much, Umberto. I have one comment. From the hyperarchimedean copula, Peter's idea, I think this is extremely cool in the sense that, at least to me, this is a generalization of a Lorentz function.
I may agree. You are the king of the Lorentz function.
So in that case, that is even more interesting to me. And the other thing is just a comment on the Kolmogorov means. Yeah. You know that, and this is something that I told also to Peter, and he was really amused by this fact that I think this is one of the results. It's a fundamental result by Kolmogorov. Actually, you say Kolmogorov Nagumo. But there is also a discussion between Chisini, Bonferroni, and De Finetti. Everyone is saying that they were the first one giving the result. And it's also funny.
I keep the side of De Finetti.
Yeah, and the fact was that Kolmogorov was writing in French, Nagumo in German, De Finetti in Italian. They were quarreling about who was the first. Yes.
Just let me make a comment on the copula, which is my field. There are results of generalization of generators that are imposed on other generators. They were made by Genet, but they were product generators, so generators which are decreasing. In this case, the idea that Peter had was to impound absolute sum, so a generator which is increasing to a copula which has generators that are actually decreasing. So the phi there are decreasing function. If I impound that, I impound a generator which is increasing, and you get very interesting stuff. I managed to reproduce copulas that are already known and new copulas with very strange properties.
Thank you, Umberto.
Thank you.
Thank you, Agnès. Okay, so it is my pleasure to introduce the last speaker of these 3 wonderful days.